This is lecture number 27 in the FOA lecture series. This lecture will cover fiber optic data links. A fiber optic data link consists of a transmitter which takes an electrical input and converts it to an optical output using a source, typically an LED, laser diode, or VCSEL. The light from the transmitter is coupled into the fiber with a connector and transmitted through the fiber optic cable plant. At the far end, the light is coupled to a receiver where a detector converts the light into an electrical signal, which is then conditioned by the receiving equipment. Most links use two fibers, transmitting in opposite directions for full duplex operation. Some systems, like fiber-to-the-home PON systems, use one fiber bidirectionally, using wavelength division multiplexing. Just as with copper wire or radio transmission, the performance of the fiber optic data link can be determined by how well the reconverted electrical signal out of the receiver matches the electrical input to the transmitter. The ultra-pure glass used in making optical fiber has less attenuation or signal loss at wavelengths in the infrared, beyond the limits of the sensitivity of the human eye. The fiber is designed to have the highest performance, bandwidth, or signal capacity at these wavelengths. The particular wavelengths used in typical fiber optic systems, 850, 1300, and 1550 nanometers, correspond to wavelengths where optical light sources, lasers or LEDs, are easily manufactured. Some advanced fiber optic systems transmit light at several wavelengths at once through a single optical fiber to increase the data throughput. We call this method wavelength division multiplexing. Fiber optic sources are typically LEDs or mostly lasers now that signal transmission has moved to higher bit rates. LEDs can be used for multi-mode fiber lengths of under about 100 megabits per second, while VCSELs are used for multi-mode lengths from 1 to 10 gigabits per second. For single-mode systems, we use Fabry-Perot or DFB lasers. These are extremely fast, extremely high-powered lasers that have characteristics that make them better for long-distance single-mode transmission. One of the big differences between LEDs and lasers is the spectral output of the device. LEDs have a broad spectral width, which causes them to suffer chromatic dispersion. Lasers have a much narrower spectral width and don't suffer chromatic dispersion as much. But on very long single-mode lengths, which we're talking about 100 kilometers or more, chromatic dispersion can still be a problem even for a laser. The type of source used in any given type of link is going to be determined by the speed of the network and the distance it must operate over, which of course also determines the type of fiber used. So short multi-mode links will typically use LEDs, while higher speed or longer links will use lasers on single-mode fiber. Receivers use semiconductor detectors to convert optical signals to electrical signals. The type of photodetector used is going to be determined by the wavelength of the light. Silicon photodiodes are typically used for short wavelength lengths, 650 nanometers for plastic optical fiber, and 850 nanometers for glass fiber, while longer wavelength systems usually use indium gallium arsenide detectors as they have a lower noise and faster response than germanium, a detector which is typically only used for long wavelengths and power meters. Very high-speed systems may use special detectors called avalanche photodiodes. that use high voltage techniques to get extremely high bandwidth. A fiber optic data link works by transmitting from the transmitter to the receiver. The source and the transmitter couples a certain amount of optical power in the fiber, which is then diminished by the attenuation of the optical fiber and losses from connectors and splices in the link. Only so much of the transmitted power is received at the receiver, and it is the receiver power that determines the performance of the data link. If the power is too low, the signal-to-noise ratio will be bad and the bit error rate will be high. If the power is too high, the receiver will saturate and the signal will be distorted, so the bit error rate will be high. So the proper received signal in a fiber optic data link is determined by the minimum and maximum power at the receiver, where the bit error rate with the signal-to-noise ratio meets the requirements of the data link. So the two main specifications that concern us in a fiber optic data link are the output power at the transmitter and the input power at the receiver. The difference between the typical transmitter output power and the required minimum receiver power is called the loss budget for the link. And if the maximum transmitter power is more than the maximum receiver power before it overloads, there's a minimum amount of loss that the link must have in order to operate properly. That's why many short laser-based telecom links actually use attenuators to reduce the power at the receiver. Optical power in a fiber optic data link is measured with a fiber optic power meter calibrated at the wavelength of the source used in the link. It's attached to the source with either a reference patch cord or the patch cord that's used to attach the source to the system, and the output power of the source is measured in dBm, decibels reference to a milliwatt. At the receiver, the cable to the receiver is unplugged from the receiver and plugged into the power meter, and again the power measured in dBm. The difference between the transmitter power and the receiver power is the loss budget for the link and must be within the specifications for that data link. Some data links may use wavelength division multiplexing to expand the information carrying capacity of the fiber. Wavelength division multiplexing, or WDM, puts different channels of data on the fiber at different wavelengths or colors of light. What we call dense wavelength division multiplexing uses very closely spaced wavelengths around 1500 nanometers, and coarse wavelength division multiplexing puts a smaller number of channels at broader spacing in the whole range between 1300 and 1600 nanometers. Many systems today use wavelength division multiplexing. Fiber to the home passive optical network systems, for example, use wavelength division multiplexing to send different signals simultaneously upstream and downstream. Downstream, data and digital phone is transmitted around 1490 nanometers, and 1550 nanometers is used for systems that use analog cable TV type video. Upstream, the signals go at 1310 nanometers. So systems with passive optical networks can have as many as 3 different wavelengths in the system at one time. Future developments will even give each home or apartment. Every subscriber can have their own wavelength. Wavelength division multiplexing systems sometimes require either special fibers or special testing. A new class of fibers called low water peak fiber reduces the water absorption bands around 1400 and 1250 nanometers to allow a broader spectral range to be used for coarse wavelength division multiplexing. Long wavelength systems worry about water peaks out beyond 1600 nanometers, but both may be testing to measure the spectral attenuation of the fiber over a broad dynamic range to ensure that WDM systems will work. High-speed fiber optic data links have to worry about dispersion, especially if they go longer distances over fiber. Multi-mode, it's typically modal dispersion caused by the different modes in multi-mode fiber, or chromatic dispersion caused by the spectral width of the source. For single mode, it's chromatic dispersion for very long lengths, even with lasers, and polarization mode dispersion, where the different polarized modes of light travel at different speeds in the fiber, that causes problems. In long single mode links, these are typically tested to ensure proper operation. In multi-mode links, where it's very hard to test, it's more likely that the link length will be limited by the standard for that particular transmission system. Sometimes one needs to use a fiber optic data link in a particular application where copper or wireless doesn't work. One typically starts with an electrical input, so it's easy to find fiber optic media converters that convert electrical signals on copper to optical signals on fiber for almost any kind of network, and these allow you to create your own custom fiber optic data link for your application, replacing a copper cable or a wireless link. More information on fiber optic data links and fiber optics in general can be found on the FOA website, www.thefoa.org, and particularly in our online guide to fiber optics. We're the FOA, the Professional Society of Fiber Optics.